I taught myself algebra and a little grammar, and somehow I scraped a high enough score on the ACT to be admitted to Brigham Young University, even though I had no formal education. This is the young, celebrated author, Tara Westover. Algebra is that basic, essential, and omnipresent. Let us explore what may be algebra of functions. Let us first get the meta-algebra. It is the mathematics of variables and extends over the entire domain of mathematics that uses the most foundational arithmetic operations. Symbols for quantities is its signature presence and play. The more mundane algebra helps us quantify relationships of specifically unknown quantities. Functions, or more simply equations, are the best face of algebra. Expectedly, functions present themselves for most extensive yet simple algebraic manipulations. At the most basic level, an algebraic expression is identified by the inclusion of the four operations and/or rational exponents. Yes, this is the much familiar polynomial functions such as x squared plus 2 square root x, x cubed 2x plus 1 divided by x minus 2, x minus 2 to the power half, and so on. Not just these, functions that are as such classified as non-algebraic, such as trigonometric functions, logarithmic functions, or the exponential functions, mostly have the four operations and exponents. Algebra is in the DNA of functions. The algebraic nature of functions is very different from what may be called the algebra of functions. At the same time, it is as simple as ABC that algebra of functions must be about applying the four operations on functions themselves. That is, addition, subtraction, multiplication, and division of functions. On the whole, algebra of functions is similar to the algebra of numbers. Of course, there is difference between algebra of numbers and algebra of functions that comes along with expressions representing numbers. One unique aspect of mathematics is that it is 100% about quantification, about giving one precise measure or count of things, relationships, or situations. The most complicated of calculus expression is solve to get a number of some kind. The difference with respect to numbers is in the arithmetic of symbols and getting used to them. Recall, success in algebra of numbers requires a good number sense. For example, broadly knowing that 89 plus 79 would be near 170, that is nearly 10, and 20 less than 100 plus 100. In a similar way, success in algebra of functions requires a good expression sense. For example, seeing that x squared is just x cubed divided by x. Pertinently, the visualizations of the different place values of decimal numbers and of the terms of functions are quite similar, in the way that the different place values are independent yet related to the other place values, just as the terms are. For example, in x squared plus 2x plus 3, the three terms show a gradation of power over x. What may be causing turbulence in addition and subtraction of functions is the very core of how we add or subtract. Recall, we can only add or subtract like things. Thus, we cannot add x squared and 3x or subtract 3 from 3x. X squared and 3x and 3 and 3x are not like terms, they are not the same things, and they do not represent same things. In fact, there is an interesting twist here in favor of functions. Addition and subtraction of numbers is, in a way, more complex, because with numbers we often try to make them alike to be added. With terms of functions, unlike terms cannot be made like terms. For example, 1 by x cannot be treated to be x. Thus, addition and subtraction of terms of functions is done with more ease and certainty. There is no manipulations possible. Function operations are straightforward. Only like terms can added or subtracted. The lesson to carry forward from multiplication of numbers that is relevant for multiplication of functions is loud and clear. Each term of one function must be multiplied to all the terms of the other function. The individual product terms are then added together to get the resultant function. Once again, like product terms will be added together to get the resultant function. Recall, when we multiply 234 and 456, we multiply 200 to 450 and 6, then multiply 30 to 450 and 6, and lastly multiply 4 to 450 and 6. We get 9 individual products and add the like products. For example, all the hundreds are added together. Also recall, 234 is 200 plus 30 plus 4, and 456 is 400 plus 50 plus 6. Thus, there is just no difference in multiplication of functions and multiplication of numbers. The story of division of functions is no different from the division of numbers. The same long division method works. A relevant reminder of the similarity is in how 300 divided by 40 is kind of dividing 7x squared plus 3x by x. We could multiply 40 by 7 as the first step, and we will multiply x by 7x as the first step. However, division of functions takes some bit of getting used to, and for that, it takes practice. Algebra of functions is about putting functions through addition, subtraction, multiplication, and division. Algebra of functions and algebra of numbers are very similar. Interestingly, the operations on functions can be graphed. To be true, it makes real sense to see the effect of operations on graphs, far more clarity and insight into the basic change introduced by the operations. Also, rather than showing how to graph functions, which is essentially a mechanical process of finding ordered pairs, x and f of x, we better explore how graphs change due to operations on them. We would see the effect of the simplest of x and y, Cartesian graph y equal to x. And then we visualize y equal to x plus x, that is also y equal to 2x. The effect is similar. For each value of x, the value of y, that is the output of the function, is double of x, not just x. Visually, it is the graph, the line, getting towards the y-axis, getting steeper, to reflect that y is increasing at a faster rate for each change in x. The graph is the simple division operation on y equal to x. The graph is y equal to x by 2. Now the function output, y, is half of the value of x. That is, for each value of x, the value of y is half of what it used to be when y was equal to x. Visually, it implies that the line will not rise up to the level of y equal to x. Recall, the value of the y-axis determines the vertical rise of the graph. The more the value of y for every x, the more vertical the graph. More towards the y-axis, more steep. Thus, the graph of y equal to x by 2 will be less steeper than the graph of y equal to x, and by implication, more towards the x-axis, turning around the center in clockwise direction closer to the x-axis. The visible degree of steepness of graphs of functions can predict the shape of the graph of the function y equal to x squared and y equal to x squared by 2. Recall how 2x, that is double of x, has a steeper graph than x. Expectedly, the graph of x squared becomes so much steeper, that is, towards y-axis, that it becomes a curve, as in the picture, the inner curve, the blue one. And what would be the curve of x squared by 2? Obviously less steeper than x squared curve. And in a curve, the less steepness is seen as a more open graph, a wider graph. The value of y in x squared by 2 is half the value of y in x squared for every x. Learning functions through their graphs is not only easier, but also intuitive after some practice. And that intuitiveness about functions is a gift. In fact, many functions and operations are better visualized before being analyzed. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.